Give maybe like 2 more minutes for this. All right, so let's go over now. See some right answers. So a couple. So he will accidentally use a negative solution, I think. Anyways, so if the width is W, the length is L. The width is 1 centimeter less than 10 times the length. So then W is 10L minus 1. Immediately, I'll just go over this for quickness. So the area is 60 centimeters. So then L times W, which is 10L minus 1, so 60. 10L squared minus L minus 60 equals 0. This actually is factorable if you try doing it. If you plug it into the quadratic formula, the discriminant is 2401. This is something I forgot to touch upon earlier. But if the discriminant turns out to be perfect squared, then you know that the quadratic actually was factorable, assuming that everything's like integer coefficients, of course, or rational. And then so if you try and go back and factor it, you get 2L minus 5 times 5L plus 12, I believe. Although you can go ahead with the quadratic formula if you can deal with this being 49 squared is what I believe it is. All right, so your two solutions are 5 halves and then negative 12 fifths. Obviously, dimensions can't be negative, so it's going to be 5 halves is what you want. So then I think I saw someone get something divided by 5. So then, yeah, that's not it, right? So then L would be 5 halved and W would be, sorry, let me just quickly respond to this. W would be equal to 10 times that, which is equal to 25 minus 1. So then that would be 24. So, you know, it satisfies the 1 less than 10 times its length condition. But but just to make sure you plug it back into the area condition, 24 times 5 halved is equal to 12 times 5. That's 60 centimeters squared. Yeah, paying attention to the units, although they don't cause any trouble here. So the parameter would just be 5 plus 48 is equal to 53. All right, I saw someone type in 548. I think that's what they meant. All right. And yeah, that's just how you did this. It's just a word problem with the quadratic involved to solve it. A lot of times, yeah, if you get an answer that's not so nice, you can use a calculator. Like you don't have to evaluate those radicals themselves unless they tell you to leave them there. Well, yeah, that's an example on how you do it. All right, so the next problem. Sum and product of roots, right? So note that every quadratic can be written as a times x minus r times x minus s, where r and s are the roots. This is because, again, a times b equals 0 implies a equals 0 or b equals 0 and vice versa. And the a and b here and here are the two quadratic linear factors, x minus r, x minus s. And if you expand this, you find the linear coefficient is negative a times r plus s, and the coefficient constant term equals a times r times s. And what this means is that the sum of the roots of any quadratic is negative b divided by a if you solve for r plus s, and the product of the roots to solve for rs is c over a. This is known as Vieta's formulas for quadratics. There are generalized Vieta's formulas for higher degree polynomials too. Oh yeah, that's just Vieta's formulas. Again, if ax squared plus bx plus c is the quadratic form, the sum of the roots is negative b divided by a. Product of the roots is c over a. Do not forget this negative sign, please. So yeah. That being said, quickly find the sum of the reciprocals of the roots of the quadratic. As a hint, you want to express 1 over r plus 1 over s if these are the two roots of this quadratic using a common denominator, and then you see where you can go from there. You see how that ties into Vieta's formulas. All right, this should take a couple of minutes. Right, I'll just go over this now. You write this under a common denominator, then you get r plus s divided by r times s, right? And from Vieta's formulas, you know that this is negative b over a over c over a. So it's just negative b over c. And then you plug b and c in, so that's negative 7 over negative 18. So you get negative 7 over 18, which I'm pretty sure is like pretty much all the answers I've seen so far. So yeah, it seems like people have grasped how to do this. Mainly the difficult part is like expressing this in terms of these maybe and noticing that, but yeah, that's just how you do it. That's how use Vieta's formulas to find expressions like that. Expressions like the sum of the reciprocals or like the sum of the squares of the roots, etc., can all be found using Vieta's for the sum and product of the two roots. So yeah, it's just a quick thing. It actually gets tested often as you go higher up into math competitions. Vieta's formulas, sum of roots, etc., tricks like that. So yeah, just make sure you know it. All right, so these are some in-class problems, although I don't think I'll go over these. I'll just probably throw these into the homework. But for now, I'll go over the last topic for today, which is substitution again. There's some more exercises on this, but I'll go over those next time. So here are two interesting and similar uses of substitution. They involve quadratics, although it might not be immediately apparent at first. So if you see a pattern that repeats, try setting it as a variable. So what it means, like, if you have the square root of 6 plus the square root of 6 plus the square root of 6 plus dot 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 nested like that, then it means it goes on forever. So then if you set this as your variable x, then you see like, oh, well, on one hand, you have that this is x. I'll just, but then on the other hand, you also know that this small part inside is x. So then you can set up an equation like that. And so similarly with this one, this you set this is x. But then on the other hand, you also have that, sorry, this part down here is equal to the x you want. So given that, you can set up quadratic equations, well, yeah, they become quadratics really. And so yeah, I just want everybody to go ahead and quickly do these two problems. I'll give like maybe several minutes until the end of class for this. But yeah, just quickly try to solve these and see what they turn out to. I think the first one should be like an integer, while the second one might not be. So yeah. All right, so I'll go over these now. So for the first one, the quadratic you get is x equals root 6 plus x, right? Because this stuff on the inside is x. So then you just make that substitution. So then you square, you get x squared equals x plus 6. X squared minus x minus 6 is equal to 0. So then you have x minus 3 times x plus 2 is equal to 0. Now, which solution do you pick? Well, consider what happens is if you try to approximate this, meaning that like it's where you have these infinite number of square roots, right? But if you cut it off only a finite number, it'll like approximate the answer. So first, if you have only one, it's root 6. If you have the second, it's root 6 plus root 6. Third is root 6 plus root 6 plus root 6 plus root 6. And now you know that square roots are all positive. And you see that root 6 is less than 3. So then this is like, it's getting closer and closer to 3, not negative 2, because like the square roots, you can't possibly get a negative number out of that. And in fact, same thing with this, it's even more clear. Like, let's say the first step is 1/2, then it's 1 over 2 plus 1 over 2, which is what's that, 1 over 5/2, so that'll be 2/5. 1/2 is 2/5. You can see they're all positive numerator and denominator in the fractions. There's nowhere's a negative number going to pop out. So in reality, there's only one solution to this as well, and I'll go over that as well. This one is quite the same idea. It's just that it's not a rational number solution. But yeah, so the reality is like x equals 1 plus 2, 1 over 2 plus, plus 1 over 2 plus 1 over 2 plus dot dot dot, and then you have this is equal to x. All right. So then you have x is equal to 1 over 2 plus x. So then you have x squared plus 2x minus 1 is equal to 0, from which you can complete the square, and then you can get x equals -1 plus minus root 2. But if you take the plus, then you get the positive solution, -1 plus root 2. The other solution is negative, so it can't be. Because as I said again, you only add stuff in the fractions in its denominator in this repeated fraction if you take the partial sums. So it can't be any negative number. So yeah, it's -1 plus square root of 2. So yeah, and those are those are what they evaluate to, 3 and -1 plus root 2. Funny thing, you can actually plug it back in a check. Like say you wanted to see if 3 really worked. Well, you can try like root 6 plus 3. And yeah, that indeed gives you 3 back for x. And no matter how many times you do it, it'll still like work out to the same number. Like if you do root 6 plus root 6 plus 3, and you get root 6 plus 3 back because it's root 9, and then you get 3. And same thing actually if you try like 1 over 2 plus root 2 minus 1 equals 1 over 1 plus root 2. And if you rationalize the denominator, that just becomes root 2 minus 1 as desired. So yeah, that's a quick way to check it. And yeah, so that's all. We'll assign some problems like this, of this style for the homework, as well as the problems we didn't cover in class today. So yeah, that'll make it most of the homework. And please, if we end up having to have more things like submit your answer in this form, please read the whole entire problem statement on the Google form before you go to submit it, because we don't want errors like that happening again and making people's scores get lower. So yeah. Yeah, so anyways, class is over for today, and yeah, I'll stop the recording now.